Welcome to the first post-recording and what would have been the 13th pre-recording of the Programming Languages Virtual Meetup. My name is Connor Hoekstra, and in this video we're going to be covering Chapter 3.4 of the Structure and Interpretation of Computer Programs. This chapter section is entitled Concurrency. Time is of the essence, and it consists of two subsections. The first one, 3.4.1, is entitled The Nature of Time in Concurrent Systems, and that's followed by 3.4.2, Mechanisms for Controlling Concurrency. The chapter section starts out by stating, we've seen the power of computational objects with local state as tools for modeling, yet as section 3.1.3 warned, this power extracts a price, the loss of referential transparency, giving rise to a thicket of questions about sameness and change, and the need to abandon the substitution model of evaluation in favor of the more intricate environment model. The central issue lurking beneath the complexity of state, sameness, and change is that by introducing assignment, we are forced to admit time into our computational models. Before we introduced assignment, all of our programs were timeless in the sense that any expression that has a value always has the same value. The text goes on to state, here successive evaluations of the same expression yield different values. This is referring to in the textbook where they have the same expression evaluated twice, yielding two different values. This behavior arises from the fact that the execution of assignment statements, in this case assignments to the variable balance, delineates moments in time when the value changes. The result of evaluating an expression depends not only on the expression itself, but also on whether the evaluation occurs before or after these moments. Building models in terms of computational objects with local state forces us to confront time as an essential concept in programming. And finally, this brings us to the first subsection of Chapter 3.4, the nature of time in concurrent systems. So the text goes on to basically set up this example involving two bank accounts and two individuals, Peter and Paul. We won't read through this, we'll just look at the visualization of it. So I guess this example only has one bank account. The preceding example has two bank accounts. So here, Peter is going to take out $10, Paul is going to take out $25. This is a joint account starting with a balance of 100, but note that because this system is not dealing with the concurrent nature of withdrawals, at the end of the day when we should end up with $65, 100 minus 10 minus 25, we actually end up with 75 because these two interleave and happen at the same time, and the $10 withdrawal gets overwritten by the $25 withdrawal. So this is setting up the fact that we need to figure out a way to deal with these situations. The text goes on to state correct behavior of concurrent programs. The above example typifies the subtle bugs that can creep into concurrent programs. The root of this complexity lies in the assignments to variables that are shared among the different processes. We already know that we must be careful in writing programs that use setbang because the results of computation depend on the order in which the assignments occur. With concurrent processes, we must be especially careful about assignments because we may not be able to control the order of the assignments made by the different processes. If several such changes might be made concurrently, as with two depositors accessing a joint account, we need some way to ensure that our system behaves correctly. For example, in the case of withdrawals from a joint account, we must ensure that money is conserved. To make concurrent programs behave correctly, we may have to place some restrictions on concurrent execution. And the rest of the chapter essentially is going to describe different types of these restrictions and sort of the pros and cons of each. So the first one is stated in the text as one possible restriction on concurrency would stipulate that no two operations that change any shared state variables can occur at the same time. This is an extremely stringent requirement. So this leads us to using this restriction, and this is the example with Peter and Paul and two bank accounts. So note that the first column represents Peter's actions, the third column represents Paul's actions. Bank 1 is the joint account, and Bank 2 is a bank account that only belongs to Paul. And the point that they're saying is using this restriction where sort of any action that is changing variables locks up any other action, that this action where Paul is depositing, the D stands for deposit, the W stands for withdrawal, where he's depositing $5 into this personal account shouldn't lock up anything else. So this is an overly sort of restrictive system. The text then goes on to state a less stringent restriction on concurrency would ensure that a concurrent system produces the same result as if the processes had run sequentially in some order. So this is a lot looser of a statement that will be less strict, but still give us the results we want, as it states. So this brings us to the first exercise, 3.38. Suppose that Peter, Paul, and Mary share a joint bank account that initially contains $100. Concurrently, Peter deposits 10, Paul withdraws 20, and Mary withdraws half the money in the account by executing the following commands. So Peter's going to call set bang on balance and do a plus 10. Paul's going to do a set bang and a minus 20, and then Mary's going to do a set bang and going to then divide the existing balance by 2. So A, list all the different possible values for balance after these three transactions have been completed, assuming that the banking system forces the 3 processes to run sequentially in some order. And then B, what are some other values that could be produced if the system allows the processes to be interleaved? So you don't need to state all of them, just some of them. So for A, I had the following to spice things up because this is a pretty simple question. I did this in APL. All you need to know is that you start with 100, you read right to left, there is a minus 20, a divide by 2, and then a plus 10. So this is not an exhaustive list of the permutations, but it is the exhaustive list of resulting values. So for the first one, we start with 100, subtract 20 to get 80, divide 2 to get 40, plus 10 to get 50. And you can read through these to get the resulting values, but they are 50, 45, 40, and 35. For question B, I have a correct value. So this basically is due to the interleaving missing out on the plus 10. So we're dividing by 2. And getting 50 and then subtracting 20, which gets us 30. But this actually isn't the worst case. And the only reason I know this is because it came up in the actual meetup on Monday, and this is a post recording, so I can report about it. So basically, if we go back, the fact that this division by 2 has 2 references to balance means that we can end up with this balance being 80, this balance being 110, and then we get 80 minus 110 divided by 2, which is 55, and then 80 minus 55 is going to be 25. So actually, the worst case is 25, not 30, but 30 is still a possible value that we could get. So the fact that I've put this comment, the worst case would be sort of makes this wrong, but this as one of the examples or one of the values that you can end up with is still correct. This brings us to the end of the first subsection, which is the shorter of the 2 subsections. It's only about 7 pages. And to the last subsection, mechanisms for controlling concurrency. This one's about 2 to 3 times as long. So now we'll focus on this. The text at this point reads a section called Serializing Access to Shared State, and says serialization implements the following idea. Processes will execute concurrently, but there will be certain collections of procedures that cannot be executed concurrently. More precisely, serialization creates distinguished sets of procedures such that only one execution of a procedure in each serialized set is permitted to happen at a time. If some procedure in the set is being executed, then a process that attempts to execute any procedure in the set will be forced to wait until the first execution has finished. So this is extremely important when we get to one of the next exercises, as there was some confusion about what serialization of a process actually does. Note that it's talking about if you have a process or procedure that is serialized within a set. So a procedure in the set will be forced to wait. Any procedures outside of the set of procedures that have been serialized aren't affected. And that'll be important in answering one of the exercise that's coming up. So here, the text gives this example of defining a local variable x to 10, and then it gives us this parallel execute procedure with 2 different lambdas that are going to evaluate in some order. So we're squaring our value in our first lambda and adding 1. It's a little bit irritating because I couldn't find a way to run this parallel execute method. I did see in the Berkeley lectures, the STK scheme dialect did have a version of it, but I couldn't find that one. So unfortunately, we sort of fly blind in answering these questions because we can't actually run this code. Comment in the section down below if you find a way to run parallel execute, and I will post that or mention that in a follow-up video. This creates 2 concurrent processes, P1 and P2. and depending on the way that they are interleaved, you'll end up with the following 5 values. So 101 and 121 are the ones that will always be possible. That's 101 because you're squaring 10 and then adding 1, and then 121 is adding 1 to get 11 and then squaring that to get 121. And 110, 11, and 100 are all values where you've interleaved and messed up. So these are the 5 possible values that you can get. It then goes on to say if you serialize your lambdas in this parallel execute, so you have this S, which is make serializer, and then we now have a set of 2 different quote-unquote procedures in our parallel execute. You can only get the 2 correct values, 101 and 121. And I believe this brings us to our next exercise, exercise 3.39, which reads, which of the 5 possibilities in the parallel execution shown above remain if we instead serialize execution as follows? So we still have X being set to 10, and we also have S from our most recently seen example, but now we use S in the following ways. So similar to the last piece of code we saw, the second lambda is just being serialized normally, but the first lambda is a little bit trickier. We have this sort of inner lambda being serialized, but the setting of X is not serialized. So I put the following. The first 2, obviously, because they're the correct answers, are possible. And I believe 111 are also possible. So 110 is not. And the reason that I got 100 wrong was for what I referenced before. So the instance where we get 100, we have basically read our initial 10, squared it, and then this is all in the serialized. So this second lambda can't start. But once we have finished this serialization, we then basically have the statement set bang x 100, and that hasn't been evaluated yet. And at this point, we're left with a single lambda where no part of it is serialized, and then the serialization of the second lambda. And at this point, anything can happen because, as the text mentioned earlier, it's only procedures within a set of procedures that will prevent each other from running and data racing. But when you only have one procedure serialized, that means that you don't really have a set of procedures. A set of 1 is just, it doesn't block any other procedures. So when you end up with lambda, parentheses, set bang x 100, and then the serialized second lambda, you can end up with basically any answer from here. So that's why you can end up with 11, because you could immediately kick your second lambda off, read 10, and then +1, do the set bang of 100, and then overwrite that 100. Or you could finish this one first and then do the set bang of 100 afterwards and end up with 100. So 111 plus the 2 correct values are what you would end up with. Moving on to the next exercise, 3.40, give all possible values of x that can result from executing the following. So we have define x10, and then 2 lambdas inside our parallel execute, one that is squaring and one that is cubing. And then it goes on to state which of these possibilities remain if we inserted use serialized procedures where they're both serialized simply. So this one's a lot more straightforward than the previous question. The answers are 100, 1,000, 10,000, 100,000, a million for the cases where they can interleave and you can get wrong answers. But for the correct answer, the only thing you can possibly get is 1 million. Moving on to the next exercise, 3.41, it says Ben Bitdiddle worries that it would be better to implement the bank account as follows, where the commented line has been changed. I'll show the code for that in a sec. Because allowing unserialized access to the bank account can result in anomalous behavior. Do you agree? Is there any scenario that demonstrates Ben's concern? So the following code is here, and this is the piece that's been changed. We've shown this code earlier in the text. If you've read the text, where basically we have a modified make account procedure that is serializing the withdraw and deposit procedures in the dispatch procedure. So this code is basically adding serialization to access to the balance. So it's saying, is this necessary? Is Ben Bitdiddle's concerns valid? The answer, no, it's not a mutator. So there's no need to serialize. There was a member in the meetup that pointed out technically if you have a method that is mutating and it's not like an atomic mutate. So if you are incrementing the value of balance by constantly adding 1, so if your balance is 100 and you're adding 50 to get 150, and you do that by constantly doing a +1 where you can get 101, 102, and then you do a read while that mutation is happening, technically, then serializing this would be useful. So it depends on the implementations of your withdraws and your deposits, but based on the way that they're implemented, this shouldn't be an issue. And moving on to exercise 3.42, Ben Bitdiddle suggests that it's a waste of time to create a new serialized procedure in response to every withdraw and deposit message. He says that make account could be changed so that the calls to protected are done outside the dispatch procedure. That is, an account would return the same serialized procedure which was created at the same time as the account each time it is asked for a withdrawal procedure. I will show the code for this in a sec. The question then goes on to ask, is this a safe change to make? In particular, is there any difference in what concurrency is allowed by these two versions of make account? So here is the original code on the left. Note that we just have a single let binding of protected to the make serializer, and then we're passing, we're sort of wrapping our withdraw and deposit procedures in the conditional expression. Whereas in our second example, we have the same outer let expression, but then we also have let expression that's binding protected withdraw and protected deposit to the evaluation of protected withdraw and protected deposit here, and then using those in the conditional expression. So we're doing the binding and the serialization of our withdraw and deposit in a let expression as opposed to doing it in the conditional expression. And the question is does this enable a different kind of concurrency, or does this change anything? And the answer that I had is the extra let expression will create an additional frame in the environment model that we saw in 3.2, chapter 3.2, but other than that, they are the same. At this point, the text goes on to state something about implementing serializers. We implement serializer in terms of a more primitive synchronization mechanism called a mutex. A mutex is an object that supports two operations. The mutex can be acquired and the mutex can be released. Note that there's a footnote commenting on this. The term mutex is an abbreviation for mutual exclusion. The general problem of arranging a mechanism that permits concurrent processes to safely share resources is called the mutual exclusion problem. Our mutex is a simple variant of the semaphore mechanism, which was introduced in the THE multi-programming system developed at the Technological University of Eindhoven and named for the university's initials in Dutch. The acquire and release operations were originally called P and V from the Dutch words, I apologize for the pronunciation, passeren, to pass, and vrijgeven, to release, in reference to the semaphores used on railroad systems. Dijkstra's classic exposition in 1968 was one of the first to clearly present the issues of concurrency control and showed how to use semaphores to handle a variety of concurrency problems. So cool to know what mutex stands for and sort of the history behind semaphores and the words acquire and release and where they came from. So here is the code for make serializer. It's pretty straightforward. We have a let expression binding for creating a mutex, which uses make mutex, and then a lambda, which takes some arguments with the define, which is going to be returned at the end, serialized P. So we're basically just passing in a procedure, and then we have two different operations. We can acquire or we can release. So basically what you would expect based on the previous description. Then we have the code for make mutex. This is where the actual sort of work of locking things up and preventing data races is happening. We have this cell, which is going to be a flag that's set to false or true based on whether a serialized procedure is being run. And then we have our internal procedure, the mutex. And this has a conditional expression inside. If we are trying to acquire, it basically calls this test and set. If it returns true, it means that the mutex has been acquired already. And so it's going to do basically what's called a spin lock, where it's just going to retry by recursively calling the mutex with the acquire message again until it's able to successfully get, it's successfully able to access and do whatever it needs to do when the mutex isn't acquired. So at this point, if we jump down to test and set, you can see if the cell is true, then just return true and spin lock. Otherwise, set car to true and then return false, meaning that we're going to end our spin lock here. And then in the second clause of our conditional expression, we are releasing and just clearing the contents of cell where we're setting this to false. So it's a lot of code here, but it's actually pretty simple to understand what's happening. And this brings us to, I believe, the last exercise of chapter 3.4 that we are going to cover. Exercise 3.47, which reads, a semaphore of size n is a generalization of a mutex. Like a mutex, a semaphore supports acquire and release operations, but it is more general in that up to n processes can acquire it concurrently. Additional processes that attempt to acquire the semaphore must wait for release operations. Give implementations of semaphores in A in terms of mutexes. And then there was a B, but we're not going to do that for this question. So here is my implementation of a semaphore. Note that it says this is incorrect at first. So this is very similar to our make mutex, except we're just calling it make semaphore. We have a let binding where we're initializing a count of the number of quote unquote acquires that we have for our semaphore. Then we have an internal procedure very similar to the mutex, except it's called the semaphore. And we've got the same conditional expression that's checking if our message is acquire or release. If it's release, we're just subtracting 1. If it's acquire, we're checking is the count of our semaphore currently equal to or greater than or equal to. I guess we should never be in a state where it's greater than. So equal to n. If so, spin lock. So just do the recursion and pass the acquire message to the semaphore. Otherwise, set count and add 1 to it, and then we're returning the semaphore similarly to how we were returning the mutex. The problem with this solution that you might have already thought about in your head is that we haven't done anything to prevent data races on count. So we have to have a local mutex to protect count when we're doing +1 and -1s from it. So the correct solution is a little bit more verbose. In our let expression, we are binding lock to mutex here. And then in each of our conditional expression clauses, we are locking and releasing or acquiring and releasing the lock mutex. So in the first conditional expression, when we're trying to acquire, we lock before we enter our if expression. And then based on whether we are going to just recurse, if we're recursing, we release it right away and then just recurse with the acquire message. Otherwise, we do a +1 and then we release. And in the clause where we are dealing with the release message, you can see that we're just acquiring before we subtract 1 and then releasing afterwards. And this will prevent data races on count. So this is the correct solution. The next section of the chapter 3.4 deals with deadlocks, which has to do with when you have, 2 mutexes that are required for some process or 2 different processes, and then we'll call those A and B. And the first process is waiting for A, the second process is waiting for B, and so these 2 things are never going to free up, and then you end up in this deadlock. So the thing that we're going to highlight here is from a footnote that talks about a way to, the text talks about a way to deal with this, but the footnote sort of mentions that and then mentions even more. So we'll read that. The general technique for avoiding deadlock by numbering the shared resources and acquiring them in order is due to Havender. Situations where deadlock cannot be avoided require deadlock recovery methods, which entail having processes back out of the deadlock state and try again. Deadlock recovery mechanisms are widely used in database management systems, a topic that is treated in detail in Gray and Reuter. So providing a couple resources if you want to read more about this. The text then goes on to read, mechanisms such as test and set, bang, require processes to examine a global shared flag at arbitrary times. This is problematic and inefficient to implement in modern high-speed processors, where due to optimization techniques such as pipelining and cache memory, the contents of memory may not be in a consistent state at every instant. In contemporary multiprocessing systems, therefore, the serializer paradigm is being supplanted by new approaches to concurrency control. So note, when it says contemporary, keep in mind that this book was published and written in the mid-80s, 1986 to be exact. So this is, at least at the time of this recording in 2020, roughly, 34 years ago? So obviously contemporary has changed, but if we go to the footnote, it reads, one such alternative to serialization is called barrier synchronization. The programmer permits concurrent processes to execute as they please, but establishes certain synchronization points, barriers, through which no process can proceed until all the processes have reached the barrier. Modern processors, note again, modern in 1986, provide machine instructions that permit programmers to establish synchronization points at places where consistency is required. The PowerPC, for example, includes for this purpose, two instructions called sync and EIEIO, which stands for enforced in-order execution of input-output. And the reason that I mention this before wrapping up the coverage of Chapter 3.4 is that in C++20, we just got stood barrier. So 34 years later, when a book is mentioning that this is sort of a different technique for dealing with coordination of threads and synchronization, we're getting this in the standard, in the C++20 standard. So if you're interested, I'll leave a link in the description down below, but neat to see a book from, over 3 decades ago mentioning a technique that is actually making its way into standardese of certain languages at this point. And with this, that covers everything I have to say about Chapter 3.4. Unfortunately, MIT didn't have any lectures that corresponded to Chapter 3.4. There are 2 Berkeley lectures. I can link those down below. I don't have anything to highlight from those, but they do a very good job of distilling what you've read in the text if you were fuzzy about anything while reading through it. So, as always, thanks for tuning in. I hope you enjoyed and learned something, and I look forward to seeing you next week for what is hopefully going to be a super exciting chapter, Chapter 3.5 on streams.